Let's return once again to our census data. Remember, we had a couple of different kinds of interpolations of that data. So the blue curve is the piecewise linear curve. The dots are the actual data. And with the piecewise linear approximation, or interpolation, I should say, the curve only feels local effects. So the value of the interpolant here depends only on the two neighbors nearby. It doesn't depend on any sort of larger trend. On the other hand, the black curve is the global polynomial interpolant, and that certainly feels things globally, but much too strongly. So things that are going on at the left end can actually still affect everything that's going on at the right. So we'd like to somehow split the difference between these two, maybe. We'd like a method that does take into account what's going on everywhere, but doesn't get hung up on every single small deviation or make these wild oscillations near the ends. And so one way, the most common way of doing that, is by doing what's known as a data fitting, where you don't try to have a curve that passes through all the data. Instead, you try to have a curve that represents the data well. In statistics, this technique goes by the name of regression. And regression is certainly a major form of what we would now call machine learning or even artificial intelligence. So our strategy for data fitting, least squares data fitting, is to pick some sort of standardized form for the function that we're going to use in the fit. So it has some empty open parameters in it, but it's otherwise well defined. And then we'll define some sort of error on how well it approximates the data, minimize that error. Now, at this point in the discussion, we have to do a notation shift. So previously, we labeled these points as going from t0, y0 to tn, yn. Well, now we're just going to find it more convenient to stick with a different numbering of those data points. So the first one will now be t1, y1, and the last one we'll call tm, ym. So with that new naming convention, let's let f of t be some candidate for our fit. So we want to know, how well does f do the job? Well, there are a number of ways we could define how well f is doing its job. So one way is to look at the difference between f evaluated at ti in the data point, okay, and then simply ask, what's the maximum deviation of that sort in absolute value? Okay. Another way we might do it is to say, well, let's look at the difference between the fitting function f and the target data y, but we'll take the absolute value and add them up over all the points. Or we could even decide to do things in sort of a root mean square way, where we square up all these individual pointwise errors, add them up, and then take a square root of the whole thing. So we'll easily see that these are familiar friends for us. If we make this definition of a vector phi, okay, so phi is an m vector consisting of the values of this candidate function f at the points t1 through tm. So phi is now an m by 1 vector, just like y is an m by 1 vector of the data. Then these three types of error before are really just the three vector norms that we've played around with. So, the maximum of the difference is the max norm or the infinity norm. The sum of all the errors is the 1 norm, and then the square root of the sum of the squares is the 2 norm of all those errors. So we might choose to minimize any one of those particular errors. But it turns out that, and there are applications where you do any of those. There are valid choices, situations where you want to choose those. But for our purposes, we're going to focus entirely on the 2 norm. And that's where we get this term least squares. We sum up the squares of the errors, and we want to minimize the sum of squares. It just turns out that that's the most mathematically convenient and the algorithmically easiest to solve. It leads to a linear problem for us to solve, which the others don't. Okay, so in order to make that nice simple conclusion to the problem, we have to make one more big assumption. So this vector phi, remember phi consists of the values of the candidate fitting function, whatever it is. And now we want to be able to claim that we can write phi as the product of a matrix A times X, where this matrix A depends on the T locations, the T1 through Tm, but not on the data. Or anything else for that matter. So if we can do that, right, if we can write phi in this form, m by n matrix times an n by 1 vector x, then we simply plug phi in, or we plug ax in for phi above, and this is what we get as our, what we call now a linear least squares problem. It's linear because the thing that we're minimizing over is x. X represents some parameter vector, and it appears only linearly in the problem. So let's make this more concrete with an example. One of the most classic things you want to do is to fit a straight line. So if we said our candidate functions consist of all functions of the form x1t plus x2, that's all linear functions. Well, we can write that in the form that we want. So the vector phi, right, is x1 t1 plus x2, and then x2 t2 plus x2. Right, and that, I'm sorry, we have m points. I don't know why I stopped at 2. I shouldn't have stopped at 2. So that should continue down to, sorry, this is an x1 here, x1 tm plus x2. So remember, phi is the value of f at all the different t1 through tm. Okay, and that vector we can write in the form of a times x, where a and x are defined here, right? So we simply have a linear combination of those two columns of A. We could extend that to the case where f is any polynomial in T. So a polynomial is a combination of Tn to the minus 1, Tn to the minus 2, and so on down to T and 1. Those parameters we'll call x1 through xn. And as we've seen in the past, when we did van der Waals matrices, a polynomial can be written in terms of a linear combination, where you take the columns that represent evaluations of the individual monomial functions, and you put all the coefficients of the polynomial into the vector x here. And in fact, polynomials are one of the most important cases, but the only thing that we really care about is a linear combination structure, right? All we really need to be able to do is to have f be a linear combination of known functions, okay? These functions may be nonlinear functions of t. And in fact, we saw that with the polynomial. It doesn't matter because we can still write phi, which is x1 g1 of t1, and so on through xn gn of t1. And then as we go down the rows, we just increase the index on t. And we can still write that as a linear combination structure, where we take g1 evaluated at all the points for the first column. We would have g2 in the second column, and so on, gn in the nth column. So it's quite a general form for this problem. The key, again, is to be able to take these parameters, the x's, that describe the whole family of candidate functions, and separate them out so that they affect the problem only in a linear fashion. Now, there are some other cases where we can do some transformations that allow us to extend to even more kinds of problems. So for example, here's an exponential fitting function. F of t is equal to a times e to the bt, where a and b are considered parameters. So in other words, we want to consider all possible functions of this form for different values of a and b. Well, that is not expressible as linear combinations with using a and b, the unknowns. But if we take the log of both sides, and here we're always going to use natural logs for our logarithms in this course. So we take the log of the right-hand side, that's the log of a product, so it's the sum of the logs. And that's log of a plus log of e to the bt is just b times t. So we can recognize this as, if we call this parameter x1, and we call b, now we call that x2, we're back to the case of a straight line fit. But it's not that the original function is a straight line fit, it's the log of the candidate function, which is a straight line fit. So we must fit the log of the data. Or if we have a power law, like f of t equals a times t to the b, again, the trick is to take the log of both sides. So we take a log of a product as the sum of the logs. So we get b times log t using the power rule for logs, or the exponential rule for logs. So now we can call this x1. We call this b x2. And now we would call this to be the function g2 of t. Right, so we have a linear combination of the functions g1, right, or that's just 1 really for all values of t. But we do have x1 times g1 of t plus x2 times g2 of t. So if we were to write this out, right, the matrix A, okay, would consist of evaluating g1 at all the different points in the first column, evaluating g2 at all the different points in the second column. So that's log of t1, log of t2. Okay, those are our only two columns. X consists of the two parameters x1 and x2. Okay, and then we fit, since we had to take the log of f, we have to fit that to the vector log y1, log y2, and so on. So with these transformation tricks, we can sometimes take a genuinely nonlinear problem and turn it into a linear problem. On the other hand, there are fitting functions that are intractably nonlinear no matter what you do to them.